Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast lecture, we're looking at our second reaction mechanism, that is the SN1 reaction mechanism, substitution nucleophilic unimolecular. Now, the SN1 reaction mechanism, unlike the SN2, has multiple steps, and we're going to begin by drawing out all the steps of the reactions, and then we'll begin talking about the key features. Step number 1 is often called ionization, but sometimes it is also referred to as carbocation formation. In this reaction, we're going to start using the same alkyl halide we used for the SN2, and that way we can compare them more readily. We'll have a delta plus on carbon, a delta minus forming on bromine. Make that a little clearer. Double dagger indicating a transition state. This is bond breaking. I'm going to call this transition state 1. And when we are done, we will have produced an intermediate species called a carbocation. A full positive charge, that, plus Br minus. Step 1 is ionization in the SN1 reaction mechanism. The transition state shows the bond that is breaking, and ionization initiates the reaction. Now step 2 we're going to look at a little later, but for right now, step 2 will always be rearrangement if possible. So we'll look at examples of this a little later on, but in this case rearrangement does not occur. We'll discuss what that means a little further on. So rearrangement if it is possible. Now, step 3 is nucleophilic attack. And in step 3, our nucleophile we're going to use is water. And the water acts as a nucleophile attacking the carbocation we formed. So I will draw the carbocation. And so what we get then is a transition state that looks like this. So delta plus here. Bond is forming to the carbocation. Again, this is a double dagger for transition state. And we have a bond forming. All right, down here, bond forming. Bond forming, and this will be called transition state 2A. The transition state for the Step 1 was transition state 1. So when this is done, I end up with, I hope I have room, I'll try to squeeze it in. Full positive charge on oxygen. C bond to hydrogen. Bond to CH3. And a bond to a CH2. CH. There we go. But because of the shape of the carbocation, it is equally possible for the water to attack the other side. If it does so, I'll go through this kind of transition state. Again, there's a delta plus on oxygen and a delta plus on carbon. We have a transition state, I'll call this 2B. Transition state 2B. And again, we have a bond that is forming. Right there. And so if I draw the final structure, I get an H, CH3, and a CH2, CH3, with an oxygen, a hydrogen, lone pair, and a plus. Now what you see before you is two products that form. So step 3, nucleophilic attack, because you can attack either side, generates an equal amount of each, of opposite chirality, a racemic mixture. Lastly, step 4 is not really part of the SN1 reaction mechanism at all. It is a step which occurs whenever you have a cationic species that is less stable than neutral and you have the availability of losing a proton. So when water attacks, you can see if I pull an H off this, I will get an alcohol. And so this is just a protonated alcohol. And so the last step, step 4, happens when it has to. It's just simply called deprotonation. I'm not going to draw a transition state for it, but indeed, deprotonation does have a transition state, like any other step of a reaction mechanism. But in this case, it's a pretty trivial step. It's just the loss of a proton. And so we're going to omit the transition states. So what you see here, minus H plus, indicating the loss of H plus from the oxygen, which produces our alcohol. And we just lose our proton. And I could certainly have drawn a transition state for that step, but to expedite matters, I will not. And then we can draw it for the other enantiomer, the same step. And there you have it. So in the SN1, we see 3 steps. Ionization, followed by rearrangement, followed by nucleophilic attack. Step 4 is a step that will occur for any reaction mechanism that produces a protonated, less stable species. Loss of the proton will occur through deprotonation. In this case, we generate the more stable alcohol. Now we can list the key features of the SN1 reaction. So let's go through a list of key features and then let's begin to talk about them. Key features of the SN1. Well, step 1, or point 1, the reaction is unimolecular. What does that mean? That means the formation of the transition state in the rate determining step. Rate determining means slow step. Is dependent on the concentration of only one of the substituents or reagents. Sorry, not substituents, I mean reagents. So, unimolecular reaction means that the formation of the transition state in the rate determining step or slow step is dependent upon only one of the reagents. 2. This mechanism involves carbocation intermediates. It involves rearrangement, if possible. 4. Unlike the SN2, this is a multi-step mechanism. Involving more than one step. Point 5. Chiral molecules give us a racemic mixture or a racemate. Point 6. The carbocation formation is rate determining. Point 7. Tertiary is faster than secondary, who's much faster than primary and methyl. Primary and methyl generally go an alternative mechanism. Lastly, overall, the reaction is favored by weaker nucleophiles, lower reaction temperatures, and very importantly, polar protic solvents. Okay. Well, let's begin with point 1. And point 1 and point 6 are very related. Point 1 states that the reaction is unimolecular. The reason it's unimolecular is one of the steps is actually much slower than the other. Now, why would having a slow step have anything to do with the number of molecules involved in speeding up a reaction? Well, there's a simple analogy I can give towards this, and I'd like to take a moment just to read this analogy to you. If you're taking this course through me, you have a copy of An analogy referred to as rates Galileo and Jupiter. An analogy. And it would be handy if you paused this video at this point and took out that handout. In rates Galileo and Jupiter, an analogy reads the following. In any multi-step procedure, there is often one rate-determining step, a step that takes so long that all the other steps have little or no effect in overall length or duration in the procedure. On October 18, 1989, the space shuttle Atlantis launched the Galileo space probe towards Jupiter. In actual fact, the flight involved several complicated planetary and asteroid flybys. Past Earth twice, Venus once, and past two asteroids, Gaspar and Ida. The atmospheric probe separated from the main orbiter on July 13, 1995, and began its descent into the Jovian atmosphere on December 7, 1995. The descent in the atmosphere was monitored by the orbiter for 57 minutes until contact was lost. During this descent, a wealth of unique and surprising data was collected concerning the chemical makeup of the Jovian atmosphere. This voyage to Jupiter consisted of at least two steps. One step, the trip to Jupiter, was approximately 6 years long. The second step, atmospheric descent, was 57 minutes. Now suppose we viewed this voyage as a chemical reaction, and we only had a stopwatch that measured time in years. Weeks and days, not to mention minutes, were beyond the accuracy of a stopwatch. The sole step, step 1, represents the overall reaction rate. The rate equals 6 years, not 6 years and 57 minutes. The 57 minutes is so much faster than the first step, it can't even be measured by our stopwatch, and has little or no effect on the overall reaction rate. Thus, the 6-year trip to Jupiter is called the slow step, or rate-determining step. In most chemical reactions, there's often one step so much slower than all the other steps that it is the rate-determining step. Now we had step 1 was ionization. Step 2 was rearrangement. And step 3 was nucleophilic attack. In terms of our analogy, it turns out that step 1, the formation of the carbocation, was the rate-determining step. Or step 1 is so slow and the other steps are so much faster that essentially any change in rate in the fast steps has no effect whatsoever on the rate of reaction. Now if you go back and look at step 1, you will see step 1 is the ionization of the alkyl halide. The point at which alkyl halide loses its bromide. Now if you look at that reaction, what's interesting about it is there's no nucleophile involved. It's simply the bromine coming off and forming carbocation. And so only the alkyl halide affects the formation of the transition state. Only the alkyl halide affects the formation of the transition state in the slow step, the carbocation formation step. Nucleophile does not affect step 1. Increasing or decreasing nucleophile concentration will not affect the ionization. But the concentration of alkyl halide will. If I increase the concentration of alkyl halide, the chance of finding an alkyl halide that will fall apart to carbocation will increase. And so only one starting material influences the formation or the rate of formation of the transition state. And that one is the one in the slow step. Okay. This really explains point 1 and point 6. This speed of step is determined experimentally. We'll actually be seeing how a little later on. Point 2. carbocation intermediates are involved. Okay? Carbocation intermediates. This intermediate is different than a transition state. Carbocation intermediates actually have a finite lifespan. They hang around for a period of time. It can be short. It can be for milliseconds, microseconds. But the carbocation actually exists for a period of time. Now, you may find that surprising because in terms of Lewis structure, carbon only has 6 electrons. And so there's an empty orbital. In actual fact, the carbon is sp squared hybridized. And there is a 2p orbital, an empty 2p orbital, available to hold 2 electrons. Because of that, carbon has a positive charge. Now, the carbocation, because of its shape, has a lot of influence on the outcome of the reaction. It is the nature and structure of this carbocation that will influence points 5 and 7. And we will discuss those when we get to them. But the carbocation is trigonal planar, it's sp squared, having an empty 2p orbital. Now we're going to come back to the carbocation at points 4 and 7. And, point 5 and 7. Point 3 we're going to come back to, rearrangement. We're going to discuss that in a moment. It also has to do with carbocations. But we want to discuss some of the other key features first. Key feature number 4. Well, obviously, this reaction is multi-step. There's a step 1, step 2, step 3. And because it's multi-step, there actually is the formation of intermediates. So points 2 and 4 are related. Point 5, chiral molecules yield a racemate, is because of the shape of the sp squared carbocation. When a nucleophile attacks, there is equal chance of it attacking either side of the carbocation. There is no difference between the two sides. And so when the nucleophile comes in, there's a 50-50 chance of which side it's going to attack. If it attacks one side, it generates one enantiomer. If it attacks the other, it generates the other enantiomer. And you end up getting a 50-50 mixture of both enantiomers. Key feature 6, we've already discussed under unimolecular. Experimentally, the slow step is shown to be carbocation formation. Key feature number 7 has to do with the stability of carbocations. Now actually we want to talk about this a little more. Seven says tertiary is faster than secondary. Who's much faster than primary, and which is faster than methyl? Now, again, methyl and primary, it suggests, don't generally go this reaction method. Now, in a multi-step reaction rate plot, if we plot energy versus progressive reaction is just time. Okay. We can start with our reagents. So here are our reagents. And what happens is, try to draw a smoother curve this time. Get a peak. followed by a little valley, another peak, and our products. Well, actually, I guess I should put in 1/3 peak. I'll show you what that peak is. So valley, peak, products. So there we go, there's the products. Now, what we have here at the top of this peak is transition state 1, or the transition state to the first step. Here is transition states 2, A and B. And then here is a transition state I did not draw, but a transition state for deprotonation. Now this only occurs when you get a protonated product. Right here is our intermediate, or our carbocation. Let's just put, I'm going to put C plus for the carbocation. Here is the protonated alcohol, so COHH plus. The protonated alcohol from the mechanism. So let's just draw an arrow to here so you know that C plus is carbocation. What determines how fast a reaction goes is the height of the hills. In fact, it's the height of the highest hill. Because this height, this high hill height, it determines how fast the reaction is. This largest hill represents a slow step. It is this hill that determines the speed of the reaction. And hence, it is the structure of transition state 1 that we must look at. What's interesting, though, is you'll notice that if you read any discussions of rate in a textbook on organic chemistry, they talk about the intermediate, the carbocation. The carbocation is not at the top of a hill. He exists in the valley. He has a lifespan, a lifetime. It may be milliseconds, microseconds. It may be for seconds. But he hangs around for a while. Why do we discuss the stability of the intermediate carbocation to explain rate if it's a transition state that controls the rate? Well, go back and take a close look at the transition state. You'll see bond breaking between carbon and bromine. But what you'll also notice is there's the delta minus on the bromine and a delta plus on the carbon. That means the carbon in the transition state has some carbocation character. A little delta plus, a little positive charge. So anything that stabilizes the carbocation will also stabilize the formation of this transition state. Understanding this is a prerequisite to being allowed to use a carbocation to explain the control of the rate. The only reason we can talk about the stability of the carbocation and the speed of the reaction is because transition state 1 is like a carbocation. So whatever stabilizes our carbocation will also stabilize our transition state. So, what that means, if we focus on just the first part of the energy diagram, where the reagents go up and you get your valley. When you go from tertiary to secondary, you get higher transition state and the same effect on the intermediate. When you go to primary, you keep getting higher. So when the intermediate is lower energy, the transition state is also lower energy. And the two parallel each other. Okay. Well, given now that we know we can talk about the intermediate carbocation, in controlling our rate, let's write it down again. Tertiary is faster than secondary, who's much faster than primary, and so on. Why? What about the tertiary carbocation makes it more able to go faster by this process? Well, let's draw it. Here is a tertiary carbocation. Here is a primary carbocation. We'll even skip the primary. Why don't we just make a methyl carbocation? Take the two far extremes. What about the tertiary carbocation that makes it form faster? Well, first off, anything that helps stabilize the positive charge will lower its energy. If you stabilize the positive charge and lower the energy, you will increase its rate of formation. Carbon is much larger than hydrogen. Because it's larger, it is more polarizable. Do you remember what polarizable means? Polarizable means it is more able to respond to a changing electric field. It can better direct its electrons towards a positive charge because it's larger. Larger orbitals allow for more electron movement. Carbon, because its very nature, can donate electron density through its sigma bond. This process is called inductive electron donation. The methyl groups are better able to do inductive electron donation. Effectively, it neutralizes this large positive charge a small amount so that the charge is a bit smaller than that on the carbon, which has hydrogens. Hydrogens cannot inductively donate this charge. There are also two other factors which we'll learn about when we revisit this material in second semester. They are hyperconjugation and steric assistance. But for now, we'll stay focused on inductive electron donation. Now, you might ask a question. Wait a second, if we have inductive electron donation, electrons being donated through the sigma bond, won't that reduce the positive charge? And won't a reduced positive charge slow down nucleophilic attack? Shouldn't this make the overall reaction slower, the nucleophile being more attracted to the larger positive charge? Well, in actual fact, you're absolutely right. The smaller charge will slow down the nucleophilic attack, but remember our steps of reaction. Step 1, Step 2, Step 3. If you scroll back, or if you've drawn out the reaction steps, look at them. What was step 3? Step 3 was nucleophilic attack. That step slows down, but that step's super fast. Let's use our analogy. Suppose step 1 was 6 years. And suppose step 3 was the 57 minutes. What if we slowed down our step 3? So that's no longer 57 minutes, but it's now 3 hours. How's the reaction rate differ if your stopwatch can only measure years? It doesn't. Now think about what happens to step 1. If in step 1 we get a smaller positive charge, the carbocation forms faster. Less charge means faster rate of formation because of lower energy. Suppose then that our 6 years becomes 3 years. Now you see a rate change. See, minutes and hours compared to years might represent what's happening in the chemical reaction, except we might be talking the difference being milliseconds versus microseconds. Step 1 is the rate determining step. It is a slow step. It doesn't matter what happens to a fast step, whether it's slowed down or sped up. It's the slow step. So if nucleophilic attack slows down, doesn't matter because it's in a very fast step. But what matters is whether we speed up or slow down the slow step, step 1. And since we have a smaller charge due to inductive electron donation, stabilizing that carbocation, it's better able to stabilize the positive charge. A lower energy forms it faster. So the stability of the carbocation explains why tertiary is faster than secondary. This inductive electron donation explains it. And it works, and we can look at an intermediate. It's carbocations, remember, an intermediate. We can look at the intermediate and not the transition state for only one reason. And what is that reason? Because a transition state is like the carbocation. The transition state had a delta plus. So we talk about it in terms of the carbocation. All right. Now, after point 8, we had, I believe, stated, or that was point 7, that overall the reaction is favored by weaker nucleophiles. Why weaker nucleophiles? Well, one of the things you don't want to happen, let's say in a secondary alkyl halide, is you don't want the nucleophile being so strong it comes in real fast. It may take some time for the alkyl halide to fall apart. So essentially, by using weaker nucleophiles, you slow down the nucleophilic attack, giving the molecule time to ionize. See, if nucleophilic attack occurs before ionization, you're going to have the SN2 happen. And so, by using a weaker nucleophile, you buy more time for the alkyl halide to ionize. Polar protic solvents are more polar, and more polar favors ionization. The more polar the solvent, the more likely you're going to ionize. Unfortunately, there's a solubility limit for the alkyl halide, and that solubility limit is that alkyl halides are not soluble in water. The best we can do is a water-ethanol mixture, representing probably the most polar system you can get an alkyl halide to dissolve in. But by using a polar protic alcohol-water system, you increase the chances of ionization because the solvent solubilizes ions better than aprotic solvents. And so, using a polar protic solvent will speed up the reaction. The lower temperature, again, is to avoid those mechanisms which are favored by higher temperatures. Now that leaves only one thing to discuss in the key features, and that is rearrangement. Now, rearrangement is an effect that occurs due to carbocation stability. And we have some key points to bring out, so I am going to show an example. Let's put this guy in. And discuss what actually happens in rearrangement of a carbocation. If this molecule were to undergo SN1 substitution, the bromine would depart, giving us a carbocation. And I would ask you to consider, what kind of carbocation is this? What kind of carbocation is this? Now, when you ask what kind, you really are asking, is it primary, secondary, tertiary? Well, the carbon bearing the positive charge has 2 carbons attached to it, so it's secondary. What you can do in a rearrangement, how about a rearrangement? In a rearrangement, is you can shift neighboring groups from one carbon to another. Now, if we were IUPAC numbering, we'd number from the end of the chain. But if you want to refer to shifting a group from one atom to another and then beside each other, it's often called a 1-2 shift. And we're going to shift a group. Now, you can shift methyls, ethyls, hydrogens, but when you do this shift, there is one paramount rule that must be followed. Always shift to give yourself a more stable carbocation. If the carbocation is not more stable, you don't shift. So we're going to consider some possible shifts. For example, could I shift the methyl? Let's try it. If I shifted the methyl over, I'll keep this methyl here. I'll keep my H. And I'm going to shift that methyl over to where the plus was. When I do that, if that methyl jumps over with its 2 electrons, this carbon's now electron deficient, this carbon is positive. If I do that shift, do I get a more stable carbocation? Well, what kind of carbocation are formed? Secondary. Is secondary carbocation more stable? Better inductive electron donation? Well, it's exactly the same. Of course not. Okay, so that shift doesn't happen. All right, let's go back. Let's keep our methyl. Why don't we shift the hydrogen? Okay, I'll shift the hydrogen. If I shift the hydrogen, what kind of carbocation have I made? It's a tertiary carbocation. Tertiary carbocations are more stable than secondaries. So what we had here was a 1-2 hydrogen shift. And it generated the more stable tertiary carbocation. Now the nucleophile can come in and attack. If the nucleophile comes in now, it's going to make a different product than if it came in here. See, if my nucleophile was H2O and then I did a deprotonation step, I'd get that. If my nucleophile came in here as H2O, giving me H2O plus on it, and then I lose the H for deprotonation, I get this. Look at what you have. This is a 2-methyl-2-butanol. This is a 3-methyl-2-butanol. They're different molecules. So the 1,2 shift actually causes a change in the carbocation to yield a different product. And you have to watch for it. Always shift to more stable carbocations. Never shift to a less stable carbocation. Okay. Primary carbocations are more stable than methyl. Secondary carbocations are more stable than primary. And tertiary carbocations are more stable than secondary. Are there any carbocations more stable than tertiary? The answer is yes. If a carbocation is next door to a ring, such as a benzyl carbocation, it is more stable than even tertiary because it is resonance stabilized. And you can draw a bunch of resonance structures that show you why it's more stable. See, tertiary has inductive electron donation, but resonance actually moves the positive charge around the ring. And moving the charge around the ring delocalizes it. None of these structures exist. What exists is the resonance hybrid, some superimposition of all three structures. And if you take all these structures and average them all together, you mean you don't have a full positive charge on the CH2. What you have is a delta plus. The resonance hybrid would actually look like this. Where the positive has been smeared out over all those positions. And so you've reduced the positive charge on the carbon. In fact, this is far more effective than the inductive electron donation. So having a positive next door to an aromatic ring is more stable than having a tertiary. Another type of resonance that is more stable than tertiary occurs in allylic carbocations. This is an allylic group. And if you lose the halide and you get this is more stable than a tertiary because it's resonance stabilized. I can move the pi electrons there. Get the double bond on this side, and I get the plus over here. Now, neither resonance structure exists. What exists is the resonance hybrid, which we can't draw with Lewis structures, but we can sketch what that would be like. And that would put a delocalized pi system where there's a delta plus at each end. This is a more stable situation because of resonance than even a tertiary carbocation. So how can these prevent shifting? Well, suppose I had an alkyl halide like this guy. And suppose I say it's going SN1, and I've got 3 methyls around here. And I'm going to compare this to another alkyl halide that doesn't have the aromatic ring with the same tert-butyl group off of it. Now, let's suppose they both go SN1, so the bromines leave, giving us carbocation. What kind of carbocation do I have? Secondary. Secondary. The carbon with the positive charge is attached to two carbons. Both are secondary. And you begin by saying, okay, well, if I shift a methyl, so let's shift this methyl over. This methyl jumps and does a 1,2 methyl shift, and he comes over here. What kind of carbocation? When he brings his 2 electrons in his bond over here, the plus shifts to here. The methyl's done a 1,2 methyl shift. So this was a 1,2 methyl shift. What have we got now? Did we shift to a more stable? Yes, we did. We shifted to a tertiary carbocation. This shift happens, and now the nucleophile would attack. Can we do the same thing here? If I shift the same way, will I not get tertiary? Yes, you will get tertiary. But the difference is this C plus is next door to an aromatic ring, which means it's resonance stabilized. It means I could draw all those resonance structures moving the plus around the ring. Because resonance stabilized is more stable, shifting to a tertiary is moving to a less stable carbocation and will not happen. And so the nucleophile would attack here. So watch for resonance in carbocations. It will not favor shifting. Lastly, why is rearrangement step 2? Why is shifting occurring before nucleophilic attack? The reason is, in nucleophilic attack, the nucleophile must collide with the carbocation for reaction to occur. In rearrangement, the group that moves towards the plus is already there and next door. It's a shift. No intermolecular collision is required. And because of that, intermolecular collisions are inherently slower. The rearrangement occurs faster, and so occurs as step 2. When competing with nucleophilic attack, the rearrangement happens first. Well, that is the SN1 reaction mechanism. Interesting to note that in contrast to the SN2, there are no carbocations, so there's no rearrangements. And that was one of the key features in the previous lecture for the SN2. So you'll notice that the SN1 is a very different substitution type of reaction than the SN2. Where the SN2 was bimolecular, the SN1 was unimolecular. Whereas the SN2 had no intermediates and was one-step concerted process, the SN1 involved carbocation intermediates and was multi-step. The SN2 did not involve a rearrangement. The SN1 has rearrangement of carbocations and 1,2 shifting to give you more stable carbocations. For chiral molecules, the SN2 gave you inversion. For chiral molecules, the SN1 gave you a racemate. And in terms of relative rates, the SN2 is faster for methyls and primaries, whereas the SN1 is faster for tertiaries. Only secondaries can go either. And by choosing the right nucleophile and right solvent conditions, you can favor either SN1 or SN2 for a secondary alkyl halide. Well, we should probably begin by looking at some reactions of both, and we're going to do that in the next lecture, maybe take some time and do some reactions, before we move on and examine 2 more mechanisms that compete with substitution. And if you remember a previous lecture, you know what that is. And those 2 mechanisms are 2 types of elimination. Well, I'm Dr. Brian Lloyd, and that's my Scribblecast for this evening. Thank you for listening. I hope it's been useful.